Okay, let's get started. Okay, first announcement is that, let's see, it's one, right? I did send out an email last week about what's going on with me. This Thursday, I guess my wife's having a biopsy that's really important. So that's going to happen at 8 a.m. And depending on how that goes, I plan on being here, but there's a chance that I won't. So I think what I'm going to do is I'm going to say, officially we're having class Thursday, but by noon, does anyone leave like an hour before class to get here? Yes?
An hour, like 45 minutes.
Okay. Would noon be enough time to let you know, like, no class? Is that enough heads up? Or would 11? 11, 11:30? 11:30? Is that better? Is 11:30 better? Noon's okay? All right, so what I'm going to do is we're going to have class on Thursday unless I send out an email on Thursday by noon. Okay, so just be looking for something in your email just in case. I don't want to have a sub come in unless y'all really want a sub. I can do a sub, but if we don't have class, I'll probably direct you to something for you to do. All right, I'll give you some assignment for you to work on or something like that. All right, so it's just going to depend on how things go. All right. Okay. What else? So like days are blending together. I'm confused. Like normally walking around right now, I'm very confused. So I thought someone from this class asked me this question the other day, but that it was the other class. So I'll still entertain the question. Okay. So this was a trig sub problem I did in class, and we look at this integral and we take this root here and we have to pull a 4 out. I think I pulled a 4 out. And anyway, the thing that's important is this. We make this trig substitution, all right? And then from this, we know that the root turns into this and that the derivative is this. And so when we go to make our reference triangle, I told you to take this and create your reference triangle from that information right there, okay? And then you can answer everything you need to answer. Well, two of the other students in my other class asked the question, well, what about, like if you use this to make your triangle, this is the triangle you'll create, okay? And so if you look at this triangle and you say, well, what's secant theta? Secant is going to be this over this, so that's this, right? But up here, the second line here says that secant theta is, 3/2 secant theta is that. And so if you multiply both sides by 2/3, you get this. And they were saying these two aren't the same. And the first time they asked the question, I was like, okay, I'll look at it, whatever. So I think it's obvious that they are the same, because all you have to do is push the 2 in here, and you get it, when it goes in, it gets squared and then distributes through. So you get 4x squared plus 9. And then you just leave the 3 on the bottom, and it's the same. So, yeah. Okay, so if you were ever pondering that, which no one was, that's the answer. Okay, now today we're going to finish up partial fractions, right, in 6.3. And we did that problem in class, right, last time?
Yes.
Okay, and that problem, what we saw on that one is that it didn't require any partial fraction decomposition. I hope you had a little bit of time to maybe go back and take a look at partial fractions. If not, let's see how we do here. All right, here's the second problem we're going to do. All right, pretty messy looking, isn't it? Yeah. So we go through and we start eliminating things, like we can't use just the power rule. This is not a basic U substitution. No integration by parts here. No trigonometric substitution. Would you all agree that we can rule all those out pretty quickly? So if you're sitting there on a test and you're like trying to figure out what do I do with this, it's a rational function, right? It's a polynomial divided by a polynomial. Whenever we see rational functions, we want to be thinking maybe long division, partial fraction decomposition. That's what you want to be thinking, all right? So I'm going to start with whether or not I need to use long division. So do I need long division here? No, because the degree up here is smaller than the degree down there. So now what, right? Now what? Well, here's what I'm going to do. I'm not even going to work with this as an integral right now. I'm just going to write down the rational expression, the rational function that I'm trying to integrate. And what I'm going to try and do is factor the denominator. All right? All of the success of this method is going to depend on my ability / your ability to factor the denominator. So let's start with, there's a GCF, right? There's a greatest common factor. We can pull an x out of all the terms. Isn't that the first step for factoring anything? GCF? Okay, and then the remaining quadratic trinomial in parentheses can be factored. Okay, so let's go ahead and factor that. That is x squared plus 2x minus 1 over x, and then this should factor. What is it? 2x minus 1, x plus 2. Do we all agree? Let's see. 2x times x is 2x squared. That gives us that. 2x times 2 gives us 4x. Negative 1 times x is minus 1x, so we're going to get that 4x, take away an x, we're going to have 3x, so that's this, and then negative 1 and 2. There we go. So factoring never goes away, right? Okay, so we have factored it, right? Yeah. Okay, now I'm not factoring the numerator, because that really is not an essential part of partial fraction decomposition. The only time we might be concerned about or want to think about factoring the top is if perhaps we get, maybe this factors and we get two factors to cancel. But that's, odds of that happening are about 0, okay, for any integral I'm going to ask you to look at. All right, so now we go and we start implementing the partial fraction decomposition. And the way it works is that we need to look at the denominator and we need to look at each factor individually and kind of categorize them or classify them, like each factor. So when we look at this factor x, that is a linear factor, right? X to the first power, it's a linear factor. So I'm just going to put here linear. And then this next factor, also linear, right? Linear. And the final factor we have is also linear. So what we have in this case are 3 distinct linear factors. Does any of that sound familiar from partial fraction decomposition? Yes or no? You can say no. You can say yes. No? Doesn't? Okay. So, is everyone clear on what I've done? I've just recognized that I have 3 distinct linear factors? Okay. So let me scroll up to the notes, and I know the notes are going to look very confusing. But part A, the different cases for partial fraction decomposition, it says, look at this case. What if the denominator, that's what we have here, has n distinct linear factors? That's what we have, right? We have 3 distinct linear factors. Then what we're going to do is rewrite, all this right here is the original function. We're going to rewrite it with a sub 1 over the first linear factor plus a sub 2 over the second linear factor plus a sub 3 over the third linear factor, all the way till we get to the last linear factor. What? What does that mean? Okay, so let's see what that really means. All it means is I know that this is going to break down to be some number a, I'm going to call it capital A, over the first linear factor, which is x. Now in the notes I use a sub 1, right? In the notes I'm not going to use a sub 1 and a sub 2. I'm going to use a, b, c, d instead of a sub 1, a sub 2, a sub 3. The only reason we use a sub 1, a sub 2, a sub 3 is because if you have so many linear factors that you run out of letters in the alphabet, then you need to use subscripting. But we're not going to face that. So I'm going to just put, now I need another constant b over the second linear factor, and then finally c over the last linear factor. Does that make sense? If you have n distinct linear factors, you're basically going to break up this original problem into some constant that we don't know over the first linear factor, some constant over the second linear factor, some constant over the third. All right? And the idea is that there are numbers that I can put here, here, and here that I don't know, that when you combine these together with a common denominator, you would get this. All right? So now we need to find A, B, and C. That's what we need to do now. What's A, what's B, what's C? Now let's just think about this for a second. If you knew this number, could you integrate this term? Yeah, this would be a natural log, wouldn't it? Yeah. It'd be a constant over a linear, which that would be a natural log. If this was a constant, some number over linear again, you could do this with a natural log, couldn't you? And this one with a natural log. So if we can find A, B, and C, we're in business, aren't we? If we can find them. So let's find them. All right, so what we do next, anyone remember the next step for doing this, partial fraction decomposition? At this point, you've got this statement right here. We clear the fractions. So what we do is we multiply this side of the equation by the entire denominator, all right? So if I multiply this side by all of this junk, they cancel, don't they? And what would I be left with? Just the numerator. So I'm multiplying both sides by the common denominator equals now, for this, where'd my blue marker go? There it goes. Come on. Come on. I'll put it in here. So I multiplied this side by x times 2x minus 1 times x plus 2. So I multiplied that on that side, and it canceled out that, right? Now I multiply that on this side also. X, 2x minus 1, x plus 2. But it has to actually distribute to each term like this, right? And what happens is when we're done, we should have an expression that has no more fractions. So let's see what happens. If I multiply a divided by x times 2x minus 1 times x plus 2, won't the x's cancel, right? So all you'll be left with is that a out there, the 2x minus 1, and the x plus 2. So I have the a, the 2x minus 1, and the x plus 2. Like that. Okay? Now, what happens when I multiply the term with b in it? Just the 2x minus 1 cancels, and you have x and x plus 2, right? And a b. So b, x, x plus 2. And then finally, we have plus c, right? And then the x plus 2's cancel this time, and you have x and then x minus 1. There we go. All right. Any questions on that step?
2x minus 1?
Is it 2x? Was it 2x minus? Yeah, it was 2x minus 1. I forgot my 2. Thank you. All right. Remember, the goal is to find capital A, capital B, capital C, right? So at this point, right now, there are two paths we can go down to actually find A, B, and C. One of them, I know when I teach this in pre-cal, I call one of them like the shortcut path. It's quick, but it doesn't always work. And then the other path is longer, but it always works. So I'm going to show you both because the quick one, you want to use it when you can. All right, so the first method to do this, I'll call it method 1. Quick and easy. Easy, that's relative, right? Okay. All right, quick and easy. So here's the idea. I want to know what A is, right? I want to know what A is. I also want to know what B and C are, but let's just focus on A for a second. We have control right now of this equation in this sense. We can come in right now and we can replace x with anything we want. Because we have an equation, if we replace x with something on one side and replace it on the other side with the same thing, we should still maintain equality, right? So I'm going to try and figure out a way that I can preserve this entire term, pick an x where I will preserve this entire term, but at the same time kill this term and kill this term. So what x value can I pick that would kill these two off, but leave this one here?
Minus 10?
X is minus 2? Is that what I heard? X is minus 2 would actually, if you put minus 2 here, it would make that a 0 and kill that one. So I'm trying to preserve this one. You're on the right track, but that kills this one. I want to kill these two. X is 0. Do y'all see that? If X is 0, that's going to kill this term. And if X is 0 here, it's going to kill this term. But X being 0 here and here will not kill off this term. Does that make sense? So we're going to just be kind of clever here. I'm going to say let X be 0. Okay? This is one of the few times that you have control, all right? You have control of the problem right now. You get to choose what you want X to be. So I'm going to let X be 0. If I let X be 0, rewrite the entire equation. What does the left side become? Just -1, right? Because the first two terms are gone. Then I have A times, now that's 0, right? So just -1. And then this is 2. And then plus, now do I need to write these? No, because of the way I chose X, that 0 kills everything, so basically plus 0. So I'm just going to get rid of it. So that's it, right? So you get -1 equals -2a. And at this point, you can solve for a. A is 1/2, right? The negative over negative is positive. So we have a. And that was pretty quick, right? And easy? All right, I have a. Let's go get b. We're going to start over. Start with the same equation. Now what can I choose x to be to preserve this one while killing this one and this one? 1/2. Is that right? How are you doing that? You're thinking you got to make this one, since these have the same factor in them, and this one doesn't have 2x minus 1, you have to make this factor be a 0, right? Yeah. So you're thinking, I need to make 2x minus 1 be 0. And if you just solve this for x, you get x is 1/2, right? So I'm going to let x be 1/2. All right, now it's going to kind of suck when I do this on the left side because I'm going to have fractions, right? Okay, so x is 1/2. I need to put 1/2 here and 1/2 here. So what's 1/2 squared? 1/4 plus, let's see, 2 times 1/2 is 1, and then minus 1. So the left side is just going to be 1/4. The right side, what about this one? 0, right? This one? 0, okay? By design, by our choice of x, that's 0 and that's 0. This one's not, though. This one is b times 1/2 times, in parentheses, 1/2 plus 2, right? This is 5/2, isn't it? And then 1/2 of that. So this side over here, these cancel. You get 1/4 equals b times 1/2 times 5/2, which is really 1/4 equals, what is that, 5/4 b. And then you can multiply both sides by the reciprocal 4/5 on both sides. So what do you get? B is 1/5. So we've got B, right? And then we go get C. Does this kind of make sense, what I'm doing? So we're not really using any calculus at this point, right? There's no calculus happening here. This is all just algebra. All right, now I want to preserve this one and kill these two off. So now we'll let the x be -2. And we rewrite the whole problem. So be careful here. -2 squared, 4 plus 2 times -2, that's -4. And then minus 1. So that's the left side of the equation. This guy and this guy should go away, right? And then I plug in -2 here, right? So C times -2, and then -2, or 2 times -2 minus 1. So that's a little messy there, but I think we can figure it out. What's the left side of this equation? Left side. -1. And then what's all this stuff put together? Everything there. 10. That should be 10c on that side. And then divide both sides by 10, so negative 1/10 is c. We have found a, b, and c, haven't we? All right, so now we're ready to go after the integral. We can actually do this now. All right? So what we're saying is this. We're going to kind of go back up to this. This integral is equal to, right? That integral is equal to the integral of three different things. It's, what was it, a over x? What was a? 1/2. So watch the way I write this. 1/2 over x, okay? And then we had plus, now b over, you have to get these right. They have to match with what you said earlier. So it was b over what? 2x minus 1 was the second one. So 2x minus 1 down here, and b was what? 1/5? I know it's kind of weird to write it that way, but just do it. All right, plus the last one, which was c, negative 1/10, and then x plus 2, right? So if I want to integrate this nasty, ugly looking thing, all I need to do is integrate each of those three terms. And I can do those. Those are pretty much ready to go now. So let's see if we can do this without writing too much more. All right, so we go, this is equal to, here we go. I'm going to do the antiderivative. Now, this 1/2, this 1/5, and this negative 1/10 are all constants, aren't they? So don't they just kind of come out and just sit in the front? So I'm going to have a 1/2 here. And imagine now you just have a 1 over x. So the antiderivative of that, natural log, absolute value of x. Okay, plus 1/5, right? That's that 1/5. Now I have 1 over 2x minus 1. The antiderivative of that is what? Careful. 1/2 natural log 2x minus 1. Where'd that 1/2 come from? Yeah, this is linear, right? So you had that 2 in front. So you have to compensate for that 2 by doing 1 over a. We talked about that last time. And then this one, I'm going to pull the negative 1/10 out. Do I have to compensate for anything here? I don't, because there's a 1 in front there, right? So just natural log of x plus 2 plus c. We're done. We can put that together. That's 1/10, but we're there. I guess the weird thing is that it's kind of hard to believe that if you put these three things together that you would get that, but I mean that's just an exercise in algebra. Get a common denominator, right, and then put them together and somehow all those numbers will work out and you'll get back that original thing. All right, what do you think? So if we go through the process and we have distinct linear factors, we put a over one of them, b over another one, c over the other one, d if we have d, e if we have e. I mean, right, you know, d if we have d. Did I just say that?
Yes.
A over one, b over the other, c over the other, d over the other, if we had another one, right? Okay. It's amazing what stress does to you. Okay, I said there were two ways, right? And that was the short way. So let's look at method 2. Long, but always works. Now we're going to see an example. We're going to see an example of one problem that you can't do with the short way. So you might be asking, why would we do the long way if the short way was nice and easy? Well, you'll see. Okay, there will be something we can't use the shortcut with. All right, so the long but always works method. Let's go back to where we had already cleared the fractions and we were sitting at that place where it was, we had already cleared things out. It was like a, and I think it was like 2x minus 1, x plus 2, plus bx, and then x plus 2?
Yes.
and then cx, and then 2x minus 1. Okay, this one right here. So we were there, and this is, in the short way, we just got clever and we just picked x to be certain things, right? The long way, you actually have to multiply all of this out, right? So that's the reality of the way it's going to be. So look, here's what I'm going to do. I'm going to FOIL this first, all right? So, and I want to do this mentally. I'm going to get 2x squared, right? 2x squared plus 4x minus x, right? And then minus 2. So whatever I get from that, I'm then going to multiply everything by an a, because there's an a out here, right? So I'm going to write that down. X squared plus 2x minus 1. And then let me make sure I get this right. I'm going to have a 2x squared, but I have to hit that with an a. So I'm going to write 2ax squared. And I normally put the a behind the number, but in front of the x. Does that make sense? 2x times x is 2x squared, but then hit it with an a. All right, the middle term, or the next terms are 4x and take away x. That's going to be 3x, right? The middle terms together? Yeah. But I'm going to hit it with an a. So 3ax. And the last term would have been minus 2, but I'm going to hit it with an a. So minus 2a? Yeah. Okay. Now I do the same thing here, but fortunately for us, we don't have to FOIL because it's a monomial times a binomial. It's not two binomials. So I can just do a bx through each of those. So plus bx squared plus 2bx. Is that all right? Just pass bx through the parentheses. Same thing with the last one. Cx squared, not cx squared. 2cx squared, right? 2cx squared, and then minus cx. Okay. At this point, what we do is we collect like terms together. So please recognize that that's an x squared term, that's an x squared term, and that's an x squared term, right? So I'm going to put them all together next to one another. And I'm going to do one more thing. So let's see if you can follow this. Again, this is something you should have seen at some point in time. 2a plus b plus 2c, then x squared. So what I did was I put this one next to this one next to this one. And since they all had an x squared in them, I factored the x squared out. So if you pass the x squared back through those, you get those three terms, wouldn't you? And notice I factored the x squared out to the right instead of factoring it out front, right? That's not really normal, but you'll see why I did that in a second. Now what I do is I grab all my x terms. So my x terms, I'll do a squiggly underline for those. Squiggly underline, there's squiggly underline. So I collect all those together. I'm going to do kind of the same thing. I'm going to put a plus here, set of parentheses, and then an x. So what will be inside that parentheses? 3a plus 2b minus c. So that would give us those three, right, with the x pulled out. And then finally, I'm going to pick anything that does not have x in it. That doesn't have x, right? And that's it. That's the only one. So I'm just going to put that out here, minus 2a. All right. So the whole reason we do this is because what we have here is an equation. We have a balance, right? Something on the left and the right, they have to maintain the balance. In order to maintain the balance of the equation, we look at the x squared here, and we say to ourselves, all right, look, this is the coefficient on x squared. That's the number in front of x squared, right? And that, in order to maintain the balance, that must match the coefficient of this side, which is 1, right? And then we say, all right, the coefficient in front of x has to match, I should draw arrows here, should have to match the coefficient in front of x here, right? And then the thing out here by itself that doesn't have an x on it has to match with the thing out here that doesn't have an x on it. In order to maintain the balance of the equation, those three things must be true, right? This has to equal 1, this has to equal 2, and this has to equal -1, right? Yeah. And then what you've created here is a system of equations. You have 3 equations and 3 unknown variables, don't you? Yeah. Okay. Yeah, I guess I'll put that right here. So I have a system of equations. My system of equations looks like this. We use normally a large brace to represent a system of equations. The first equation is 2a plus b plus 2c equals what? 1. And then the second equation says that 3a plus 2b minus c must equal 2. And then finally, the last equation says that this, negative 2a, must equal negative 1. 3 equations, 3 unknown variables. And in college algebra, you're supposed to learn how to do that, right? Okay. Now, do you remember, did I ask y'all this in the beginning of class, how many of y'all had TI instrument calculators? Right, and there were a few that didn't, okay? Yeah. So who does not have a Texas Instrument graphing calculator? 1, 2, 3, 4. You don't have a graphing one? I don't think that one's going to do it. Yeah. Okay, so
I think there was an advertisement by the login computer. They say that there's like TI for $30, $40.
yeah, I don't want to make anyone go buy a calculator, you know? I don't want to. But at the same time, you know, if you don't have a calculator that'll do this, you've got to do that by hand, right? And, well, does anyone want to? Well, I can teach y'all how to use your calculator to do this, but apparently I can't teach everybody because they don't all have the same calculators.
So if we didn't use calculators last class, or Calculus 1 for doing this method, we can still do it again, right?
If you didn't what?
If we didn't use calculators last time, we can just not use it again for this method.
That's right, you can just do it by hand.
That's fine.
Yeah.
Are they usually, like, is this usually the level of complexity, or over time will it get like crazy?
Let's finish today, you'll see. I mean, yeah, let's just keep going. So this method is longer, can you agree? But it'll work. Like we won't ever run into an issue or a situation where this won't work. Okay, so let's see. Let's do this. Next class, try and bring your calculator if you don't have it. And if you don't have one, I'm going to bring some extras. I might be able to scrounge up just enough extras for the test. Maybe like 4 for the test so the people can use them. All right? We'll work something out. And I believe we can check them out across in the lab with an ID. Okay, so everyone who has theirs, go ahead and take theirs out. And I'm going to teach you how to do this on your calculator, right? For those of you who don't have one, just pay attention and maybe look off your neighbor, okay? Because even if you don't use this and you do it by hand, this will be useful later, all right? So let me start this with a small disclaimer. There are ways to do this on these calculators very efficiently. If you know how to use the calculator, you can enter it as a matrix and you can do some stuff to it. I understand that it can be done, but the problem is each calculator has different features. So maybe on one calculator it looks a certain way and on a different one it looks different, right? So the method I'm going to show you will work with all of the TIs, all right? That's why I'm showing you this way. So I'm just saying that, look, if you know a better way, great. I'm not here to reteach it. But if you've never seen this is the way you should do it. So the first thing you want to do is you want to try and bring up what's called the matrix menu. Okay, so I need everyone to find somewhere on their calculator the matrix menu. And I'm going to go around and make sure that everyone has it. Yep, okay. Yep. Yep. Okay. Y'all good? Matrix, everyone have matrix menu up? And I think along the top it says something like something math edit, something like that, right? Do y'all see that? Okay, yes, everyone there? Okay, so now I want you to go to math. What this says is we're gonna do like some sort of mathematical operation on a matrix. And then it's gonna give you a big list of things. And I want you to scroll down until you see R, R, E, F. Not REF, RREF, because those mean two different things. All right? It stands for reduced row echelon form. That's what that stands for. What we're going to do is we're going to put a matrix into reduced row echelon form. All right? Okay, so hit enter now. And you should be sitting on your home screen. It should have RREF sitting there with a parenthesis. Is everyone there? And then like a cursor just waiting for you, yes? Okay, so now all we've done right there is we've called up the actual function, okay? And we're going to need to execute this function, but we need to have an input for it. And the input is this system of equations. So the way that we first need to visualize this is as what we call a matrix, or an augmented matrix. Now, we're not here to talk about matrices. If you don't know what a matrix is, don't get bogged down with that, all right? All we're going to do is look at the coefficients. We need to make sure that we've got the A's lined up, the B's lined up, the C's lined up, and then the numbers on the other side. And we're just going to put these things in order. So I have the number 2, 1, 2, 1. Agree? Across the top, 2, 1, 2, 1. Then the next one is 3, 2, negative 1, 2. Yes? And then the last one is negative 2, 0, 0, because there's no B term, there's no C term. And the last one is negative 1. So this is what we call an augmented matrix, all right? Now, we haven't put this into the calculator yet, right? Okay. We need to tell the calculator this is our matrix. So the way we do it is this. Right here, we put a bracket, not a parenthesis, a bracket. I believe it's above the 7. I could be wrong. You have to hit like shift or something. Is it above the 7? I don't know. They're in different places. Do y'all see the bracket? Yeah, see, yours doesn't have that, right? Did it have RREF? Oh, yeah. Okay. No, it's okay. It's okay. No, I'm good. Because different ones have the bracket maybe in different places, so I can't. So everyone find the bracket? Okay, what that bracket is telling the computer is, okay, this is the beginning of the matrix. I'm starting the matrix, all right? Now, you have to put another bracket. That bracket is telling the computer, here comes the first row of numbers, all right? So first bracket is I'm starting the matrix. Next bracket is I'm starting the first row. Now you're going to put these numbers in with commas between them. 2, comma, 1, comma, 2, comma, 1. Then what do you think? Close the bracket. That's telling the computer, hey, I'm done with my first row. Next, open bracket. No comma between the brackets, just open bracket now. And now you feed it the second row. 3, comma, 2, comma, negative 1, comma, 2. And make sure you use negative 1. Don't use the minus sign, right? You know how there's a negative sign and a minus sign? Use the negative 1. What next? What next? Close bracket. Next. Open bracket. Last row. Negative 2, comma, 0, comma, 0, comma, negative 1. Close bracket. Close bracket again. So this closes the last row out. This closes the matrix out. Parenthesis closes the function out. Enter. Now, when you get your answer, depending on your calculator, you're probably going to see something that looks like this. 1, 0, 0, 0, 1, 0, 0, 0, 1. You might have to scroll over to see this. And there should be 3 numbers here. What numbers do you have?
0.5.
Are they decimals? Okay, so 0.5, then 0.2, and negative 0.1. Okay? Understand? Any question? Anyone have a problem getting that? Okay, so let's interpret the answer. If I were going to ask you to convert this matrix back into a system of equations, you know how we took that to the matrix? If I tell you take that matrix back, then this is saying you have a 1 in front of what? A. So that first row is telling you you have A, nothing, nothing equals 0.5. And the next one's telling you B is 0.2, and the last one's telling you that C is negative 0.1. And these you could all convert to fractions, right? 0.5 is 5/10, that's 1/2. 0.2 is 2/10, that's 1/5. That's negative 1/10, that's negative 1/10, right? So you could reduce those fractions, you get the same answers. Now some of your calculators gave you the answers in fractions. Anyone? Anyone have their calculator actually gave you the answer as fractions? No? Everyone did? Everyone got decimals? What is it? Control enter instead and it'll give you the fraction? Okay, yeah. All right, that's it. Okay, so this is the generic input string that you would need for any matrix. What's pretty cool about this is if you had 17 equations and 17 unknowns, you could use your calculator to solve that system of equations. Now they have to be linear equations. Like it has to be a, b, c. It can't be like a squared b and then c squared or c cubed. Those are not, that would be a system of nonlinear equations, much more difficult to solve. All right, understand? So we got the same results, and then we just plug them back in a, b, and c, and then we integrate and we're done. Let's go and do the next problem. Does that really say 140? Wow. All right. So this problem here, we need long division first because we have a power on top that's bigger than the power on the bottom. So let's start with that. So I'm going to be doing a bunch of algebra before I even go after this problem, right? So I put here division box. I put x to the 4th plus 0x cubed minus 2x squared. Does anybody own a TI-89 or the Nspire computer algebra system one? Yeah. So there's a function in that calculator. I believe it's called apart, A-P-A-R-T, apart, where you can just type this whole thing in. You can put apart and then type that in, or maybe it's called common denominator. I don't know, but it'll actually break it down. We'll do partial fraction decomposition. It'll decompose the whole thing for you. But it will also integrate it. So, I mean, if you're going to type it in, you may as well just integrate it. That's why I don't like those calculators on tests, because you can do it all, right? You can do the whole thing for you. All right, there we go. So please recognize that 0x cubed. I put that placeholder in there, right? And now we play our little game. What do we multiply x cubed by to get x to the 4th? X, okay. And then that x distributes through to each one of those. I put it under here, I subtract. So I'm going to have an x to the 4th minus x cubed minus x squared plus x. Come through and change the signs, right? Because we're going to subtract the whole row. So this is going to subtract, that becomes plus, this becomes plus, and this one becomes a minus. Doing all right today? You all right? You okay? Are you not feeling well?
No, I just can't let it be exposed to light.
Oh, okay. All right. I just want to make sure you're all right. You're usually all like energetic and stuff. And, okay. Okay. All right. Here we go. What do we have? These are gone. X cubed minus x squared plus 3x plus 1. So everything came down. Is that all right? And we go again. So what do we multiply x cubed to get x cubed? 1. So just 1, right? So 1 times that whole thing is just that whole thing, right? X cubed minus x squared minus x plus 1. Change the signs. I do it like with the big old bold so I don't like lose track of what happened, okay? Okay. All right, so I'm going to get the first terms to go away. That's by design. And then that goes away. That just happened to happen. All right? Right here, 4x. That's it. 4x, right?
So then it would be 4x over.
Yeah, so we can't make x cubed turn into 4x, so we're done with that. This is our remainder. So we put here plus the remainder, 4x, over the divisor, x cubed minus x squared minus x plus 1. Yeah. Questions? All right, so let's rewrite the original problem. This integral is equal to the integral of what? X plus 1, then plus this thing, right? Now, when we look at that integral, the first two terms we're okay with, right? We're like, okay, great, yes, got it, yes, got it. This one we don't know how to integrate. It's not a basic U substitution. There's nothing really that we have in our arsenal except now partial fraction decomposition. So now I'm going to erase this. And I'm going to take just that expression over there and work on it. So I'm just going to leave that there. I'll come back to it. I'm taking 4x over x cubed minus x squared minus x plus 1. And I'm going to try and break this down. So first thing I'll do is try and factor the denominator. I don't have an x in every term, right? But what should tip you off here on the factoring is the fact that you have 4 terms. And we do always try and factor 4 terms using grouping. Grouping doesn't always work, but it's going to this time. All right, so the way we do grouping is we look at the first 2 terms. I like to draw a little slash right behind the second term. And what you do is to the left of the slash, you pull a GCF. So I'm going to pull a greatest common factor out of the first 2 terms, which is x squared. And I'm left with x minus 1 when I do that, right? That's just pulling an x squared out of both of those. Then you pull a GCF, if you can, out of these. So y minus 1, because you need this, whatever's left over here, you're going to pull something out, right? You need whatever's left in here to match this, or else grouping fails. So you recognize that if you pull a negative 1 out, right, of this and this, then that leaves you with x minus 1. And then these two match exactly, right? So that's what we were hoping for. So this now becomes 4x over what? It's, yeah, you can write it x squared minus 1 and then times x minus 1. Or you can put the x minus 1 in front of the x squared minus 1, whichever way. All we're doing is pulling out an x minus 1 from here, from both. Now, isn't x squared minus 1 a difference of squares? So isn't this 4x over x plus 1 times x minus 1 times x minus 1? Yeah? Now, you might look at this and you might think, okay, I have 3 linear factors now, right? But if you look back at the notes, it said, what do we do when we have n distinct linear factors? Distinct meant they were different. And here we have 2 factors, linear factors that are the same. So what we're going to want to do is write it this way. We're going to want to write it like this. 4x over x plus 1 times x minus 1, that quantity squared. Okay, and that is the complete factorization of the denominator. Now the question is, how do you do partial fraction decomposition on this? Well, let's see what we have. We have this piece right here, which is linear, right? And this right here is a repeated linear, right? That's a repeated linear factor. So in the technique for partial fraction decomposition, this is what we do. Let me do it, and then I'll take you up to the notes to see it. For the linear factor that is distinct from this one, we're going to treat it just the way we did before. We're going to go a over it. Okay, so there's nothing different in that factor, right? Right? Okay, it's this second factor. Because it's squared, we don't just do b over that. Here's what we do. We do b over that other linear factor, and then c over that linear factor squared. And you might ask why, and my answer will be because this is this is what works. This is what will get us there. All right? So what if this had been cubed? Let's just think about what would this be if this was cubed. It would be b over x minus 1 plus c over x minus 1 squared plus d over x minus 1 cubed. And then you'd stop. If this was the fifth power, then you'd have to do b, c, d, e, f. Makes sense? Just the power keeps coming up. And that's in the notes, but it's so difficult to read it. Where is it? What if the denominator has some repeated linear factor? So if we have a linear factor to the k power, we'll put a constant over the linear factor, then a constant over the linear factor squared, then cubed, and we keep bringing the power up until we get to k. Does that make sense? That's what we just did on this one. We just looked at it, we said, oh, it's squared, so I'll start out with the first power, I'll bring up the power to squared, new constant, stop when we get to the highest power. That all right? All right. Now what? Clear the fractions. Multiply both sides by this. So when I multiply the left side by this, what do I get? 4x. Now let's see if you can do this without having to write it down. If I multiply this by this, what cancels? The x plus 1, and what's left? The x minus 1 squared and the a, right? Plus, if I multiply this by this, the x plus 1 does not cancel this time, right? So I have the b there. The x plus 1 does not cancel. How about the x minus 1? Only one factor cancels. So you still have a factor of x minus 1 here. Y'all see that? And then on the last one, when I multiply this by that denominator, the c is still there. The x plus 1 does not cancel. The x minus 1 squared does. So that's where we are. And now let's just try and find a, b, and c. So how about the shortcut? Is there a way that we can get a, preserve this one, and kill these two off? What would x have to be? -1. If x is -1, I can kill this and this, right? Yeah. So I can get a, can't I? Yeah. All right, can you get b, though? Can you preserve this and kill this and this? You can't. See, look, what's the only way you can kill this one off? If x is 1, right? But if x is 1, you're going to kill this one off. You're going to kill b also. You see what I'm saying? So you can't preserve b without... Well, you can't kill these off without killing that off. Can you get c? Yes, here you can let x be 1, and then it would kill these two off. So we can get a, we can get c, but we can't get b. Now you can still go down that path, but it's just a little bit messier, I guess. Not messier, just more work that has to be done. So since that doesn't work real clean, I'm just going to do the long way. I'm going to go 4x here, And then I'm just going to multiply this all out. Okay, so I'm going to do this in my head and distribute an a through. Ax squared minus 2ax plus a. So everyone understand? I expanded that. That became x squared minus 2x plus 1. Then I distributed an a through that. That's this, I think. And then the next one, when I multiply these two together, that's difference of squares. That gives me x squared minus 1. And then I distribute a b to that. So bx squared minus b. And then plus cx plus c. Am I going too fast on that, or are y'all okay? I'm going too fast? No? We're okay? All right. Let's pull all my x squareds together. Right? So I have 4x equals, let's see, a plus b, x squared. So that's these two, and I pull the x squared out the side. Let's get my x's together. Here's an x term. Here's an x term. So how do I write that? Because it's negative 2a plus c. So watch how I do this. I'm going to put plus parentheses minus 2a plus cx. So I'm always going to be putting pluses in between these things. I'll just deal with the parentheses, and that's where I'll put the negative. All right? And then I need to grab anything that doesn't have x. So that, that, and that. I have a bunch of stuff without x. So plus a minus b plus c. If you want, you can put all that in parentheses too. You don't need to, but it kind of separates the idea that, look, this right here has to be something over here, right? Questions? We get to match the coefficients. Oh, crap. Wait, what? Yeah, so if we go and look at this, I hope you've left a little bit of room in front of that. We need to realize that this is really 0x squared plus 4x plus 0, right? That's what 4x is. So the coefficient in front of x squared has to be 0. The coefficient in front of x has to be 4. And this right here has to be 0. Agreed? So I should have a system of equations now. My system of equations would be what? A plus b is 0. And when I write this, notice I'm going to leave a little space here for my c. Second equation, negative 2a plus c is equal to 4. And finally, a minus b plus c is 0. So you have 3 equations, 3 unknowns. So there are ways you can do this without the calculator. Like you could say a is negative b, right? Something like that. A is negative b, so then you could replace that with a, because negative b is a, right? And then you could solve this for c, and then get it in terms of a and plug it in here. You have an equation with a, but you can get the calculator out, okay? I don't feel like doing that. So we're going to have, what's the matrix we're going to have, the augmented matrix? 1, 1, 0, 0, negative 2, 0, 1, 4, and finally 1, negative 1, 1, 0. And we throw that into the RREF, reduced row echelon form. And look, if you do this enough, you'll kind of get fast with that. Just like bracket, bracket, da da da, comma, comma, and you get all the numbers in there, And of course, I didn't bring my calculator today. I should have told you all to bring them. So, yeah, okay. So I'm going to just wait for someone to do that. While somebody's computing that, I'm going to go back up here and rewrite the integral.